Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at Chapter 6, Thermodynamic Models of Real Pure Compounds, and we are looking at how we can mathematically use our basic definitions, fundamental relations, and Maxwell equations to recast hard problems in terms of things that are measurable. So in this video lesson, we'll be looking at some new measurable quantities. First, as a reminder, we have our fundamental relations. du is TdS minus PdV. dH is TdS plus VdP. dA is negative SDT minus PdV. And dG is negative SDT plus VdP. And each of these also tells us the natural variables for these various energy functions. From those equations, we can take the second order partial derivatives with mixed variables and develop the Maxwell relations. dt dv at constant s is negative dp ds at constant v. dt dp at constant s is equal to dv ds at constant p. ds dv at constant t is dp dt at constant v. And finally, negative ds dp at constant t equals dv dt at constant p. And our goal has been to use these in such a way that we can recast things in terms of things that can be measured. Tp and V can be measured easily. C sub P and C sub V can be measured indirectly, but that's possible. But we don't have a way of measuring internal energy, enthalpy, entropy, Helmholtz energy, or Gibbs energy. And so our goal is to use these so that we can estimate these last five in terms of things that can be measured. In this lesson, we're going to introduce two new measurable quantities. So these are not directly measurable, but kind of like C sub P or C sub V, I can evaluate these in terms of measurable quantities, and sometimes you'll be able to find tables that will list these values. I find that most often it's going to be in, let's say, a heat transfer textbook. So the first of these is the coefficient of thermal expansion. In this book, it's designated alpha sub V, and it is 1 over the volume times dV dt at constant pressure. So this is looking at the change in our volume property with respect to temperature. We also have the isothermal compressibility. It's quite similar, but we're looking at how volume changes with pressure. This is designated kappa sub T. It is negative 1 over V times dV dP at constant temperature. Liquids are an excellent opportunity to use alpha sub V and kappa sub T because these are typically very close to constant for liquids. That means that the path doesn't matter, and I can write these in terms of ordinary derivatives. So alpha sub V is 1 over V dV dt. I can separate the variables. Alpha sub V dt is equal to dV over V, and I can integrate both sides. So alpha sub V, integrating from T2 to T1, is alpha sub V times T2 minus T1 is equal to the natural log of V2 over V1. If you want it solved for the final volume, V2 is equal to V1 times the exponential of alpha sub V times T2 minus T1. We didn't have to use any skills that you didn't know very early in your calculus education. So now then, let's do the same thing for kappa. Kappa times dP is equal to negative dV over V. If I integrate from state 1 to state 2, kappa times P2 minus P1 is equal to the negative natural log of V2 over V1. This time when I solve for V2, V2 is equal to V1 times the exponential of kappa sub T times P1 minus P2. I can use this equation that we just developed if I have a change in pressure. I could use the one using alpha when I have a change of temperature. So these are very easy ways to find those modest changes in volume that I would have with a change in temperature or pressure. We know from our past experience that changes in volume based on temperature or pressure changes for liquids are going to be very small, so we would expect these numbers to be very small. Why is this worth the time to do it? Well, let's look at an example. This is an example from your textbook. An 80-liter water heater tank is initially sealed and full of water at 130 degrees Fahrenheit and 1 atmosphere. The water heater is designed to maintain the water at this temperature, but due to a fault in the temperature sensor, the heating element comes on and remains on. The temperature of the water is going to increase, but there's no space for the water to expand. It wasn't designed for that. But the tank has a pressure relief valve that's designed to open at pressure of 10 atmospheres. What temperature will this be? Now, I'm not going to go through the details. They're in the book. But let me just kind of go through an overview. We are wanting to know a change in temperature for something where what's described is pressures, temperatures, and volumes. So we are wanting to know how temperature changes as a function of the pressure and the volume. Using the definition for a total derivative, dt is dt dp at constant volume, dp, plus dt dv at constant pressure, dv. Now, temperature is a function of pressure and volume. That was the whole idea of what we were trying to figure out, right? So how are we going to do this? Again, they do this in the book, so I'm not going to repeat what they do. I assume you guys, can read this on your own. But to evaluate the dt dp at constant volume, they use the triple product rule. To evaluate dt dv at constant pressure, they use the definition of alpha. Definition, I can write, of alpha sub v, and then this is alpha sub v times v. They use that, and then they get to a form where they have dt as a function of things that are all measurable. And finally, the last step is they integrate from P equals 1 atmosphere to 10 atmospheres, and V equals the same thing. V1 and V2 are the same. So this whole dV part is actually going to be 0 in this case. And that's how they figure out what the temperature is. Now I'm going to leave this for you to read or work on your own. So this concludes this video lesson. We have one more topic that we want to discuss for this chapter, and we'll do that in our next video lesson. Thank you very much for your time.